Hi, we are the Southampton cohort of the Energy Storage CDT.
I'm Thomas Bryan. I'm Andrew Jorgaragas.
I'm Alex Holland. I'm George Hilton.
I'm Daniel Wright.
I'm Nina Meddings.
And we have been challenged to design, build and manufacture a vanadium redox flow battery for demonstration purposes. This is how it went.
The vanadium redox battery is a flow battery. There are two external tanks of electrolyte solution, one positive and one negative. The battery cell is placed between the tanks. The positive electrolyte is pumped from a tank to the one side of the flow cell, while the negative electrolyte is pumped to the other side. An ion exchange membrane in the middle of the cell keeps the two solutions from mixing together, whilst allowing hydrogen ions to pass through. While charging, V4 gets oxidized to V5 and the color changes from blue to yellow in the positive tank. In the other tank, V3 gets reduced to V2 and the color changes from green to purple. The process is reversed while discharging.
We began by thinking about the factors that were important in designing our flow battery, including vanadium concentration, the size and configuration of the battery, whether to have 2 or 4 tanks, a flow past or flow through system, what flow rate we should use, and what the current might be.
The strength of colour of vanadium solutions depends on their concentrations, according to Beer-Lambert's law. Using values for vanadium extinction coefficients estimated from the literature, we could work out the vanadium concentrations needed to give a good visual impact. The next key decision was cell configuration, and whether to have a 2-tank or 4-tank system. A 4-tank system requires complete conversion of vanadium species in one pass through the flow cell. Using values for typical charge and discharge currents from the literature, we used the Faraday equation to work out the flow rate that would be required to achieve this, which came out very low. So low, in fact, that mass transport effects might be an issue for the vanadium redox reactions. We therefore decided on a 2-tank system for our demonstrator, in which partially depleted electrolyte is recirculated through the cell. Another key decision was electrode configuration, and whether the electrolyte should flow past a 2D electrode or flow through a porous 3D electrode. Given the low vanadium concentrations involved, we decided on a flow-through system to maximise electrode surface area.
The electrolyte consists of vanadium pentoxide, which is in the form of V5, sulfuric acid and water. You dissolve vanadium, the sulfuric acid in the water. We then ran a H cell to see what colour change we got. So a H cell is basically 2 half cells divided with a glass frit. You then put 2 carbon rods in and apply a voltage. Looking at the photos here, you can see going from yellow, which is V5, going through to V4, which is a blue colour, going through to V3, which is a green colour, and finally going to purple, which is V2.
SolidWorks was used throughout the project. SolidWorks is a computer-aided design program. Using computer-aided design speeds up the design process by making it quick and easy to modify ideas before production starts. In this case, we use SolidWorks to design each component within the cell.
To manufacture the aluminium end plates, we cut sheet aluminium to size with the guillotine and used a punch to make the holes. The half cells were manufactured in the engineering design and manufacturing centre. Firstly, the carbon felt is placed within the half cell. Then gaskets are used to seal the naphthalene membrane in place between the half cells. Gaskets are then placed between the half cell and the carbon polymer current collector, and the whole assembly is placed inside the aluminium end plates. The clamping bolts are then tightened to compress the gaskets and seal the cell. 3 gasket materials were tested. The first, a simple black rubber, leaked immediately when tested with water. The 1.5mm silicon foam sealed well initially, but leaked when left overnight, and the 3mm silicon foam successfully sealed and was used for the rest of the project. Carbon felt was used as a porous electrode due to its very high specific surface area and high chemical resistance. It was cut to size and layered to achieve the correct thickness. This small half cell was selected due to its simplicity and flexibility.
Before building our final cell system, several experiments were performed to scope the performance of our cell. Changing the concentration of vanadium electrolyte will naturally affect the energy stored and performance of the cell, but important to us is how the strength of colour and charge and discharge times change. The flow rate can also be altered. This changes the amount of time vanadium ions spend in the cell, but will also determine how well the electrolyte mixes. A battery analyzer was used to charge and discharge the cell at different currents and different voltages.
For example, we can use different voltages to charge the battery, observe the resulting current profiles, and determine an appropriate discharge current. A high discharge current is desirable to achieve a fast colour change. However, it can also reduce the output voltage as well as the capacity of the battery. This reflects increased concentration overpotentials due to mass transport effects. Given the low vanadium concentration we are using, charging and discharging of our battery is likely to be mass transport limited. Increasing the flow rate of the electrolyte can help overcome these effects by increasing the supply of vanadium ions to the electrode surface, as can increasing the vanadium concentration.
The base was produced using a laser printer, so you used a thin sheet and the laser printer cut out all the holes. This was then fixed to a base, and we also then fixed a back to it and cut some holes in the back as well for the pumps. This was then sprayed white. The case manufacturing was also done in the same workshop. Perspex sheets were cut out and then put together with fixings.
This is a video of the battery charging. As you can see, the positive electrolyte tank is changing colour from green to yellow, and the negative electrolyte tank is changing colour from green to purple. This is a video of the battery discharging. As you can see, it has lit up the LEDs. The colours of the electrolyte tanks are changing back to green.